13, if you look at like 5, 12, and 13, well, if you look at the two shorter lengths, that's 5. Here's another one, that's 12. The area of this one and what Pythagoras realized is he realized that actually 25, 144, if you add those together, that will equal 169. Not that part. So that will make a nice big, which is 169. So these two areas add up to this area for it to be a right angle triangle. The square root of 169 is 13. Or I could say it's the square root of 169. So that's why that one works. So there's actually some perfect numbers that work. So that's why what I say is, when I see this, I actually do it like that in my head, Pythagoras' theorem. So, you know, if you tell me, okay, you've got two shorter lengths, I don't know, give me a number, Saman. Two numbers.
7 and 8.
7 and 8. All right, what's 7 squared?
49.
And what is 8 squared?
64.
So 49 and 64, the area of the bigger one needs to be, what's that going to be? 113, I think. Is that right?
Yeah.
So that's 113. So this length is square root of 113. Similarly, can I have another number, Saman?
14.
14. And another number, less than 14?
12.
12. Can we make it proportional? Maybe 8?
Okay.
Sorry, just so it looks a bit better. So if we've got 14, what's 14 squared? Oh, I don't know that. What is it going to be? It's going to be, what's 7 14s? And I can double that. 7 times 10 would be 40. Plus.
196.
Thanks, 196. Struggle town over here. 196, right? And what's the area of this one?
64.
64. So what does the area need to be of this one? Well, when you think about it, it's going to be the difference between these two, because these two need to add up to that one, right? So that's going to be 132. So the length of it is the square root of 132. And when you look at your math, you've been doing this the whole time. You're like, hang on a moment, a squared plus b squared equals c squared. So it's really like, oh, 14 squared. The area of that is 196. And then we knew that we didn't know b squared, so let's just still write that as b squared and write that as b squared. Then we knew a squared was plus 8 squared, which we realized was plus 64. And then we had to do the difference between these. So we knew that the area of b squared equals 196 minus 64. So let's just look at this. We go, well, I know these two squares, the area of these two squares add up to that area. I know that that area is 8 squared, that's 64. So we said that that's 64. Plus this, we didn't know that yet, has to equal 14 squared, which is 196. So then I have to go that minus that to find out what the area of that is. And that's why you subtract it on the other side. And then the last step was, well, we square root it. So b equals the square root of 132. And that's why I say it's more about 3 squares that touch each other's corners rather than a triangle. They just form a triangle, the edges of the squares. Anyway, that's one proof. It's a visual proof. To me, it kind of stuck with me. I thought it was really cool. I thought I'd try and show you guys something a bit different with Pythag, just to sort of look at it. And yeah, you can still use the formula. There's no problem with it. I like to see just different representations of that as well. So when you're kind of working through it, you should be able to justify what is a pretty good side. So again, it is a squared plus b squared equals c squared. And really all we do know that what the actual rule is, how you can actually see that is really, if you think about what a squared plus b squared is, if I want to visualize that, you could say, well, that's a squared, that's b squared. So those two areas equals to the big one. If that's true, it's a right angle triangle. Or if you know it's a right angle triangle, you can figure out the other ones. Hence A, B, and C, and they actually make squares like so. Yeah, questions, comments? Otherwise, I'm going to leave it there. You guys can't see what I'm doing, what I'm drawing. I just realized, sorry, this here. So what you can say is that a squared plus b squared equals c squared. So I'm just saying the a squared plus the b squared has to equal the area of that. Questions, comments before we move on? All good? Ish? Okay. That's one of the concepts there that you hopefully can understand. Last one is, I'm going to go quickly just through Soh Cah Toa and then I'm going to leave it with you guys. So again, we have Soh Cah Toa. And how this basically works is this only works for right angle triangles as well. And what we actually do is there's a few things we can do. So if you have a 30-degree angle, so let's do this. If I've got if this is an equilateral triangle, right? Sixty, 60, 60, 60 degrees. Happy with that? Who should I choose, Saman? Do you want to work with me or should we choose someone else?
I reckon you should go for Mahmood. He seems pretty
But
eager.
he's what about someone we haven't heard from in remote learning or someone you don't hear from?
Hunter Jonathan Greco.
No,
No, Hunter's doing his test. I
he's
reckon you
doing
should
his
choose Sanuth, maybe.
What about you choose one of the girls?
Okay, let's see. Have we heard from Haim recently?
Yeah, we have. Yeah, I've heard from her. Someone we haven't.
How about Hardra?
Oh, that's a good one. I've heard from Hardra. I was actually thinking of that. Hardra, welcome.
Hi.
Did you hear that? You're right.
No,
Sorry. No, come on, stick with me. This will be pretty easy, this one. So don't stress too much. All right. We're going to halve this triangle. Yeah, that's all we're going to do. I'm going to halve it this way. Can you see how I've just there? Yes? You with me?
Yes.
What's this length going to be?
1.
Yeah. What's this angle going to be?
60.
What's this angle going to be?
30.
What's this length going to be?
0.5.
What's this angle going to be?
90.
What's this length going to be? Can I help you with this? What's the area of this square?
1.
What's the area of this square? It's a half multiplied by a half.
Sorry. 0.25.
Which is?
1/4.
Right. What's the area of this side? These two areas, remember, I need to add up to this one.
4.
Right, and this is why I like the visual model. What's this length going to be? What do we do to get the area to that?
Root it.
We do, right? And the square root of 3 on 4 is, do you know or you want a hand?
It's √3/2.
Root 3 on 2, because you can square it to 4. That length here is √3 on 2. Okay, so that's how I remember this triangle. This is one of the triangles that you're going to need to remember for year 11. This actually will help us with exact values for circular functions later on. We're going to park that. Thank you, Hadra. Thanks, Saman. That was a good call. Haven't heard from her in a while.
You're welcome, sir.
Yeah, thanks. So that's what we got. So we found out what the lengths are. So really what we can do here is we can actually then say, well, if I've got sine 30 degrees, what does that equal? Well, here's 30 degrees. What's sine? Sine is equal to my opposite over my hypotenuse. What's my opposite here, Saman?
Your opposite.
Yeah, of 30 degrees.
Opposite of 30 degrees. I don't know. It kind of looks like a half to me.
It is a half, and a half divided by 1 is just a half. So you'll see that sine 30 degrees is a half. And here's a fun fact. What is cos 60 degrees?
Is that a half as well?
It is, because it's adjacent over the hypotenuse. They both come from the same triangle. And that's why it's a half. So if you go into your
Pretty
calculator,
interesting, in my opinion.
yeah, I think it is. If you actually, here's something that's more interesting. Before you guys actually used your calculator, they had this book. I don't know why I'm typing capitals. Book of right angle ratios. So they have this book where, oh, come on. There's the tablet. There's one of them. Oh, come on. Where is it? It was really, 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 really thick.
Oh yeah, I watched it. I saw it. It was like insanely like thick and
It's, yeah. It's huge. The thing was massive. Oh,
It's like
come on.
it's
Here it
so
is. Here's
big.
one. Yeah, I can't find the book. This is really annoying. There's one back in the day. World's first trigonometry revealed in ancient Babylonian tablet, which I thought was pretty cool.
you know, I know a person that can read that.
Oh, wow, that would be so cool.
Who might
Uh,
that be, Mahmood?
Here it is. This is
Name's
one part
Jermaine.
of it. This is one part of it where they had back in the day like a whole reference lookup for the degrees of the angles. So they actually measured out like 1 degree, 2 degree, 3 degree, 4 degree, 5 degree, 6 degree, 7 degree, 30. And if you look at 30 degree for sine, see how it's a half? And if you look up cos for 60 degrees, where's cos? Over here. Cos 60 degrees, it's a half. So they actually had all these ratios. And what they did, the first book, that one's a very easy one, that was probably one of the early editions, is they just measured out each triangle. And they made a right angle triangle. And then they made this, like, say that's maybe 5 degrees. And then, you know, that's 85. But once you know that's 5 degrees, you've also got the answer for a 5 degree and an 85 degree lookup because they both come from the sine triangle. And then they literally measured it. But they made these triangles quite big because then your measurements are a bit more accurate. And then they said, well, 1 degree increments were very good. So then they went to like 1.1. Anyway, and then there was this really long book that basically went to increments of that much of a degree. So they'll do like 1.0001, 1.0002 triangles, and they'll slightly change it. And what they actually did is they looked at the ratio of like opposite over my hypotenuse length. And then they just wrote that as a ratio. This is what your calculator does. Like if you guys go, let me tell me what sine 20 degrees is. It tells me it's 0.342. So what they actually realized is back in the day, what actually happened is they had a triangle, and just say this was like 100 centimeters long. and they measured this was, what did I say? How many degrees did I say it was? 20 degrees. And you did a 20-degree triangle. They actually realized that that was 34.2 centimeters long. They literally made these, and this is how they came up with the ratios. So they made these right angle triangles, and they go, oh, well, if that's the case, and then what's cos 20? Let me just check out what cos 20 is. And then they'd measure the whole thing. So cos 20 would be 93 point, let's go 94.0. They said, you know, this is 93 point, what is it? Let's do it, 9692. So they might say 97 centimeters. And then they realized that, okay, so the opposite of my hypotenuse ratio is 0.342. So it's 1 to 0.342. So then they said, okay, so if this is 1, that is 0.342. This is also going to be 0.939667. So your calculator has all these ratios stored in there, like as a list, and it looks it up. So that's actually what's happening. So people physically measured out these triangles and looked at the ratio of, you know, if it's from this angle, my opposite over my hypotenuse, which is sine, or my opposite over my adjacent, which is tan, or, you know, cos, adjacent over hypotenuse. And they looked at all these ratios, and that's what they did. So these don't just come from, like, your calculator's not like a genius. It came from people actually creating these triangles and finding the ratios of these. And that's where it came from. Yeah. Now we can do it a lot more easy by the use of a unit circle. And that's what we're going to look at later on. We're going to look at, okay, if I have a circle here, the radius of 1, and that makes 20 degrees, what's my height? That's going to be my opposite, which would be my y degree, which is actually sine theta. And what's my length? My length is actually my x coordinate. And if you think about that, if this is 1 cos adjacent over hypotenuse, that's going to give you your x coordinate. So we're going to look at trying to understand this and these things and exact values and how we can go start from here, we can go that way infinitely, or from here backwards. And what that actually makes where we're going, and I don't expect you to do it right now. No, not that one. This one. And what that makes is, if I put on sine, here we go, what that actually makes is this. So if I look at sine, sine is the value of the y coordinate, but basically the y coordinate starts at 0. And as we move around the inner circle, it's 2 pi and 1 pi, it's going to make this shape, and we're just literally mapping the y distance. As you can see, that reaches a maximum point there, and then it gets less. Goes negative y coordinate, goes lower, and so on. So we're going to look at that, and then we're also going to try and understand cosine. Cosine's a mapping of the x. Let me just start it again. So obviously here, it starts at 1, so it's going to start up here drawing. When it reaches here, the x value is 0. When it reaches here, the x value is -1. Here, the x value will be back to 0. So it's going to reach a value of 0. Here, when it reaches there, it will get to -1. It's here, it'll go back to 0. Here, it'll be 1. And it will reach up to a maximum of 1. 0, because it's just mapping the distance from the x. See this line here. And that's what we're going to look at doing. Don't worry if you got none of that. It really doesn't matter. We're going to go through the basics. Then we're going to scaffold you, hopefully, to get to the understanding of this one. So going back to these triangles, basically, I actually call them a ratio. So when I see Soh Cah Toa, I see this as ratios of a right angle triangle. And what I mean by that, well, if you've got a right angle triangle, it doesn't matter what the degree is. But as you change the degrees, as I increase this, the ratio of sine, which is my opposite over my hypotenuse, is going to increase. Because this is getting bigger if this stays the same. We keep the hypotenuse consistent, that's getting bigger. As this angle increases, my cos ratio is going to go down because it's the adjacent over hypotenuse. It was bigger here. As I go a smaller angle, if you think about this, my ratio for sine is going to decrease because my opposite over my hypotenuse, if I take that length divided by that length, it's going to be really small. Cos is going to be really large, so it will increase. So I actually see sine as that over that as a ratio of the two lengths for that given angle. Cos is the adjacent over the hypotenuse. And tan is the ratio between my opposite over my adjacent. Hence, when tan is 45 degrees, if you've got a 45-degree triangle, where's Hadra? You there, Hadra? She thought she got out of it. Hadra. She's checked out, has she? Saman, are you there?
Yes.
What's happened to Hadra?
Why me, sir?
No, what's happened to her? Do you
I
know?
have no clue.
No clue?
I reckon
No.
she got arrowed or something.
Oh, God, come on, that's not nice. Choose someone
No,
else.
Clearly a fireball.
Who else?
Maybe even a zap.
Who else? Another female. Who we haven't heard from.
Another female, Mahmood, maybe?
Oh, come on.
I know. Oh,
Come
sorry.
on.
I thought. Never mind. Let's see.
That's appalling.
This is. Come on.
I apologize, sir.
Go
I
for
mean,
Hadra. Oh,
Mahmood.
we got 9. Here we have Marina. We've heard from Michelle.
Am I meant to
Victoria.
choose?
Yeah.
Okay. How about Victoria?
Victoria. She did come on a bit earlier, but we'll ask her. Victoria there?
Yes.
Okay. Tan. What's tan the ratio of?
Opposites over hypotenuse.
Ah, good one. So we say Soh Cah Toa.
Oh, over the adjacent.
Yep. So I write it like this because it's already giving me the ratios. I prefer to write like that. You can write like this. There's nothing wrong with it. Okay, so it's tan is opposite over adjacent. Okay, what's my opposite here? What do you think this is going to be for this? What do you think tan 45 is going to be?
Gonna be it's gonna be the hypotenuse.
Is it? Tan is a ratio between the opposite length divided by my adjacent length. If this is my opposite length and I divide it by my adjacent length, what do you think the answer would be? This is a 45-degree triangle. What do you know about a 45-degree triangle?
It's a right angle.
It is a right angle triangle. What else do we know? What about these lengths? What do we know about these lengths? Is there anything in common?
They're the same length.
They would be the same length, right? If it's 45, would you agree it would be the same length?
Yeah.
So we call this an isosceles triangle?
Yeah.
I think I spelled that wrong. Isosceles. Okay. So we call that an isosceles triangle, right? Which means that if this is the same and that is the same, what would the opposite divided by adjacent be?
1.
Right. It doesn't matter what their lengths are because they're always the same. It doesn't matter how big that 45-degree triangle is, as long as it's 45 and 45, we don't really care. You know, as long as this is 45 and this is 45 and it's a right angle triangle, it needs to be a right angle triangle, it's going to be 1.
Yeah.
So that's why tan 45 is 1. Now, how do I get this value below 1? Would this angle, would it need to be a triangle like this, where this is the angle in question? Or would it be like that, where this is the triangle in question? Option number 1 or option number 2? Which one would get this answer to less than 1? What is tan? Tan is the ratio between what? Have you got an answer or you're not too sure?
Are you asking me still?
Yeah, still, yeah.
No. It would be the adjacent would have to be larger. I
Right.
think. So it would be number 2.
Would adjacent need to be larger? If the adjacent is larger, the adjacent or the opposite would need to be larger. Okay, let's look at this. If it's number 2, this is the opposite. Yes, and this is the adjacent. So the opposite's larger, isn't it?
Yeah.
So
number 1.
okay, so what would happen in this scenario?
It would be larger than 1.
Yeah, so tan theta would be greater than 1. And here, because the opposite is smaller than the adjacent, that's going to make a number less than 1.
Yeah.
Well done. Yay, round of applause. All right. Why I'm doing this, guys, is because I presume a lot of you have some pretty good prior knowledge of how to actually use this maths and how to solve these. It's the understanding of what we're actually doing that's really important for us to actually move forward on understanding the unit circle. We need to understand what these actual Soh Cah Toa stands for. If you don't understand that, if you can just solve it, it's not going to get you anywhere when we come around to the unit circle and try and understand that. So we need to really unpack what it represents. So don't sort of second guess this, and that's what we need to do. So just talking about there, we looked at tan. So it's the same thing we talk about sine, opposite over hypotenuse. So in this case, my opposite over hypotenuse, it's going to be a really small number. Now sine's going to be getting bigger. Could sine ever get larger than 1? Well, it can't, because if you think about it, the hypotenuse has to be the longest length, right, on the whole triangle. This is always going to be smaller than it. So a smaller number divided by a larger number is always going to be less than 1. Now, if it can get close to 1, it actually does get to 1. It gets to 1 when this is your triangle. 1, 2 lines, 3 lines. Sorry, 1 line, 2 line, and my third line is just a dot. So in other words, here is my hypotenuse. Here is my opposite. And here is my adjacent. So they're actually the same length now. So opposite of hypotenuse is the same number divided by the same number. Now, as soon as it flips over, if we keep on going around the other way, and then I go this way, again, even if we're looking at this angle in question, sorry, that's not a right angle triangle way. So as soon as it flips over the other way to that point, it would make a right angle triangle here. That's what I meant to say. It would come back to there. Even though this is your angle there, we can actually figure out what that length is, what the ratios are, but we'll get into that one a bit later. Let's not go flipping. What I want you to try and understand is that the opposite over hypotenuse, this number is always going to be less than 1. We'll get close to 1. Cos is the same thing. My adjacent over my hypotenuse, well, the hypotenuse is the highest number. That's always going to be less than 1. Tan, on the other hand, opposite over adjacent, that's going to be a small number divided by a big number. So that's going to be a small number. Then we get to 45. Let's just pretend that's 45. It's going to be 1. Then here, opposite over adjacent, it's going to be a big number. So tan has a large value, okay? And it actually has an undefined value when the adjacent's 0, because you can't divide by 0, as you guys should know what undefined means. And that would be in the same thing as this, where my opposite is 1, and then my adjacent is 0. Like if that doesn't exist, then it's undefined. And that's what we're going to use to get to the unit circle. So really, to solve these by themselves, I don't think they're too hard. They're not too challenging. I hope you guys are okay with it. If you're not, please feel free to yell out. But really, if you want to find the angle of a triangle, all we need to do is just, okay, clearly it wants me to stop drawing. Yeah, I'm going to leave it there. So hopefully that helps you with really understanding what it is and how we can find out these triangles and their value. Okay, because I'm in the footer. I did want to show you this though. So what we need to do at the end of the day is, if you do have a triangle, if it's a right angle triangle, you're given an angle, and just say, you know, that's 3 and that's 5, and I want to find out what the angle is. First thing, this is my opposite, that's my adjacent, that's my hypotenuse. We use the rule Soh Cah Toa. The first thing is to identify what ratio you're using. You're using opposite and hypotenuse. So I know I'm going to use sine, which is 3/5. Now, what's really cool is what we do, 3 divided by 5 is 0.6. Now, what we used to do, is we used to go back here and go, hey, when is sine 0.6? And you'd look up the value, so you can see signs here. So this is a bad book. Now I can see 0.6 is pretty close to 37 degrees. It's in between 36 and 37. So then I can go, well, that equals 36.7 degrees because someone measured it. But what the calculator does is we go, you know what? We do the inverse of sine. So we're going to go theta equals the inverse of sine. And when you do this in your calculator, you say, hey, tell me what the angle is when sine has a ratio of 0.6, when the opposite over the hypotenuse is 0.6. So if this was 6, that was 10, that still has a ratio of 0.6. If it was 20, and that is 12, this still has a ratio of 0.6. These are all the same triangles. It doesn't matter because the ratio is the same. And you look at the book, we just use technology this day. We just do the inverse of sine. When your ratio is 0.6, 36.9. Okay, I took a guess on the decimal. So really it doesn't matter. Like even if you do the inverse of sine, you know, let's go with like 200. Let's go with like, I don't know, it's going to be like 0.6. So it's going to be, let's go with 600 over 1,000. I mean, that's still a ratio of 0.6. It doesn't matter my opposite over my hypotenuse. It still has the same ratio. That is it. Because if you think about what angles are, like if you've got the same ratio here, and it's fixed in as a right angle, doesn't matter how big you make that, they're all the same triangle. Because if you've got, you know, that degree there, and this is a right angle, you can extend this as much as you like, but the ratios of these lengths are still going to be the same as those lengths. So that's why we use ratios, and that's why I talk about it as being a ratio of right angle triangles. So that's how you can solve it to find an angle. If you're given an angle, right, let's say it's 30 degrees, and I know that's 5, and I want to know what the hypotenuse is. Okay, so first of all, opposite hypotenuse. Okay, I want to know my hypotenuse. I've got an angle. I've got opposite, so I'm going to have to use sine. So sine 30 equals opposite over hypotenuse, which is, equal to 5 over x. And then I go, this is sine 30. Now, I know that sine 30 is a half because we looked at that before. Okay, so this is actually a half equals 5 on x. Times x out, and then divide by a half underneath. 5 divided by a half is 10. It should be x, whoops. So x will equal 10. And I also know that if that's half of that, that has to be 10 anyway. So sine 30 is one that you should know, is that the opposite is half of the hypotenuse length. But really what you're doing with the math here is you're actually looking up what the value of this is. My ratio is 1 on 2. If that's 5 on x, well, if you think about it, they can say that's x10, or if you want to think about it another way, if this is 5 on x equals 1 on 2, Well, I've got to get this to 5. I've got to times that by 5, times that by 5. That is 5 on 10 equals 5 on x. Hey, look, it has to be 10. So I'm just trying to deepen your knowledge of really what we're doing in terms of this. The calculator is just looking up these values. These values come from looking at a ratio. So actually sine is the ratio of my opposite over hypotenuse. My cos is adjacent over hypotenuse. Tan is opposite over adjacent. So they're the ratios of those. And if you look at tan 45, you'll see it's 1. Okay, and that's talked about it. In terms of Pythagoras, don't forget it's actually more about 3 squares, as you could see it, rather than actually looking at a triangle. So it's really the area of this plus the area of that has to equal the area of that if it's a right angle triangle. And then we square root it just to find out the side lengths of these squares. So 3 squares are joining around it. And that's it, guys. So really from here on in, that will be